So this is an example of generalized network flow. This company specializes in collecting and recycling paper. So they collect some used paper that goes through two types of processes, process 1, process 2, to create some kind of intermediate material, and then this material is used to produce actually the end products for newsprint, packaging and paper and print stock. Packaging, paper and print stock, 3 products. And we are given supply, demands and certain costs of processing, and also yields, which in this case indicate the loss of mass when you process a product. So if you look at these tables, when you take raw materials, there are 4 raw materials: newspaper, mixed paper, white office paper and cardboard, right? They can be converted, they can be moved to process 1 and then processed there and process 2. And as you see, processing newspaper, raw material newspaper through process 1 costs $13 per ton and gives a yield 90%. So what that means is if you have a ton of newspaper and process it, you pay $13, but you only get some kind of paper pulp that there is only 0.9 ton of it, right? Not 1 ton, but 0.9, or from 10 tons you'll get only 9 tons of a paper pulp, right? If you process it through process 2, you will get the cost is lower, it's $12, but the yield is less, so you only get 85% of the original mass at the end of this process, right? And then we are also, so we're given here for all those products, when you process them through this process 1 or process 2, we're given costs and yields, and you're also given here supplies for those for those raw materials. So we know we have 70 tons of newspaper, 50 tons of mixed paper, and so on, 30 and 40 tons of the remaining products. And now this is not the end, right? Process 1, process 2, the product after the processing through these processes is not finished. We still can we still have to process further those intermediary material to produce newsprint, packaging, paper and print stock. And again, there is a cost of taking material from process 1 and making the product for newsprint. There's a cost per ton $5, and there's a yield 95%, and you are again given some of the for each combination a cost and yield. And then there is demand for each of the final products: newsprint, packaging, paper and print stock. There is a demand 60, 40 and 50 tons. What I want you to notice is that there is a structure here for this problem. The structure is somewhat similar to the transportation problem, but not really, because if you look at it, we have 4 raw materials, right? The network can be, this is raw material 1, raw material 2, raw material 3, raw material 4, right? And then we move it to process 1 and 2, let's call those 5 and 6. These are the process 1 and 2, so there are connections here from 1 to 5, 1 to 6, 2 to 5, 2 to 6, and so on, right? Okay, and of course there will be costs here and yields, or indicating losses, right? There is a supply here 70, so we'll say minus 70, minus 50, minus 30 and minus 40. These are the supplies, and then from those processes we'll take further, right? This is process 1, process 2. We take the material further to make newsprint, packaging, paper and printing stock. So the nodes will be 7, 8, 9 for those end products, and of course there have to be connections, the arcs connecting 5 and 6 to each of the 7, 8, 9. And then here it's what we have demands, right? So it is a kind of a transshipment problem, but with generalization that introduces the yields, right? What I want you to also see is what is the total supply here. There is 70 plus 50, it's 120, 150, 190. The total supply is 190, and the total demand is 150. So it looks like the total supply is higher than the total demand. So for at the beginning we'll assume inflow minus outflow greater than or equal the supply or demand value, the BI, for the constraint. So if you want to draw this right in a nicer way, I have a slide here where I prepared this drawing, including all the information that is provided. So what you see is the 4 nodes for the raw materials, the 2 nodes for the processes. Now notice that actually cost of processing is put on the arc that goes from the raw material to the process, right? So in a sense, this node is tells us, in this node we have basically the intermediate material that is after processing but before converting it into the newsprint or packaging paper or printing stock pulp. And you can see all the costs, and you can see next to the ends of arrows you can see yields here as well, yields and costs. You can see all the supplies with negative signs to indicate they are supplies, and the demands with positive. So this looks a little bit like transportation network, but it is really not transportation because it is not bipartite. If anything, it has 3 parts, right? One part that we go from here to the second stage, and then there is a third stage. So there are 3 parts, and you can't really solve it like a transportation problem, so we still have to use the most difficult Excel format that was the version 1 or version 2 for the transshipment. So what will the model look like? Well, we have 9 nodes. We'll need to have 9 constraints. We will still have to have flow variables. We'll still have to have total cost minimization. But just remember that in those constraints now we'll have to include the yields, right? So what goes out of the newspaper is X15 and X16. But when these X15 units, when they arrive in node 5, they will be multiplied by 90% or 0.9 to indicate there is a loss on this flow. So if I move to I'm not going to write the model now to just present it. The LP model, linear programming model for this generalized network flow example problem will be Xij is the number of tons of material, but notice here now, this is important, not flowing on arc from I to j. It is really flowing out of node I on arc I to j. The difference, why am I insisting on this definition? Because now flow into node j is actually Aij, the yield, times Xij, right? So Xij really denotes what is flowing out of node I towards the node j, but what's flowing into node j is multiplied by the yield, right? The cost function is without change. We still have minimize the total cost of processing. So if there is a flow, we multiply it by the unit cost of flow. It gives you the total cost in dollars of processing here. And then let's look at the constraints. As I said, total supply is higher than total demand, so we're using inflow minus outflow greater than or equal the BI. And we're saying, right, what is if you look at, once again here, there is no inflow into this node, so inflow is 0, outflow is 1.5 and 1.6, so I have to say minus x15 minus x15 minus x16 greater than or equal supply minus 70. So effectively what it says is the sum of outflows must be less than or equal 70. And then the same for node 2, 3, and 4 for the other materials. Whatever is taken out of those nodes is less than or equal the supply amount that is provided, right? Now, what happens in node 5 and 6? These are the most interesting nodes here. In this recycling process, what arrives here, right, in process 1 is all the four products when they are processed to receive this paper pulp, some kind of paper pulp with yields, right? There is a 90% yield, 80%, 95%, and 75%. So if you look at the inflow is 90% times x15, 80% times x25, 95% times x35, and then 75% x45. And then this is going to be inflow, and then outflow is going to be, so there will be minus x57, minus x58 minus x59, and with those with the outflow we don't include the yield, right? On the outflow the yield does not play, is not used. The yield will be used when this this outflow, the units going here, would arrive at the new sprint. So be careful about this. We use the yields only when the variable is used as the inflow, not as the outflow. This is important because if you use it twice, you will basically cancel the effect of the yield completely. If I use it here, multiply the outflow by 95% and then multiply the inflow by 95%, you'll basically cancel the effect of the yield. So if you look here again at the constraint, you see this inflow for node 5, which is process 1, is 90% of something flowing in, and then so on, right? Yield times the flow, whatever units were flowing out of those nodes 1, 2, 3, 4. When they arrive at node 5, they are multiplied by yield. There is a loss, and then outflow is just a regular unit. So you see there was an outflow here without yields, there is an outflow here without yields, but the inflow here is multiplied, all the inflows are multiplied by yields. And then we say greater than or equal to 0 because this one is a transshipment node, right? There is no supply, no demand, so it has really zero value of BI, and so we say basically right, we're using inflow minus outflow greater than or equal to 0. It would be correct in this case to also write here equals to 0, but both ways will work correctly. So for the second constraint, for the process number 2, node number 6, the constraint looks analogous, and you can, I'm sure, understand if you understood node 5, node 6 should be clear. Now what do we have in node 7? It's actually a little bit easier than the previous two nodes. In node 7 we have just the inflow, no outflow, so it is X5-7 and X6-7, but remember, when it is an inflow we have to include the yields. So if you look at this, it's 95% times X5-7 and 90% times X6-7 greater than or equal 60, which is the demand in node 7. Similar constraints for node 8 and 9, and non-negativity to just say all the flows must be 0 or higher than 0, right? There are no maximum restrictions here again on the flows, upper bounds on the flows. One comment, so this completes the model. It's a little bit difficult, but I'm sure if you study it for a moment, you will see it's not. It is quite easy to understand. One complication that we have here is actually when I compared the total supply with total demand, I forgot about one thing, right? What we really meant when we were comparing this is total supply sufficient to satisfy the total demand. And before, right, there were no gains, no losses, so we said if we have 190 units, that's definitely enough to deliver 150 units, but 190 for 150. But now, recall that we have losses, right? When there is a flow here on X15, what goes out, that's only 90% of it arrives in node 5, and then when it leaves node 5, maybe 95 or 90 or something, there's another loss, right? So there are multiple losses here, and in that case, when these 190 units goes through the network through various ways, we can't be sure we really have enough for 150 units of demand. So the question is, can we really satisfy the total demand 150 having a total supply 190? If we're not sure, right, in this case we really can't be sure unless we do some additional analysis if this is enough, right? If this is what happens, then what you should do is you should assume first of all it is enough and use the greater than or equal signs in the constraints. But if you solve this model in Excel and you get an infeasible solution, infeasible problem, right, the solver tells you the problem is infeasible, I can't find any feasible solution, that means the assumption was wrong. The losses are so big that this is not enough, the supply is not enough to satisfy the demand. Then all you need to do is change this sign to less than or equal and then solve the problem again. And it's very easy to change this in Excel, and if you write a mathematical model, I would just put a note that I'm putting greater than or equal, but if it happens to be infeasible, I'll change it to less than or equal. In terms of mathematical model, you have to add this additional note. There's no other way without solving to be 100% certain that the model will be feasible this way.